Hello viewers, in today's session we are going to discuss an important problem from Fourier cosine transforms, and here in this class we are going to find out the Fourier cosine transform of a Gaussian function, right? So here we have this problem where we have to find the Fourier cosine transform of this Gaussian function, that is e raised to minus ax square, right? And in this session we'll also prove that the Fourier cosine transform of a Gaussian function is another Gaussian function, right? So let us first quickly see some concepts which are going to be used to find out the Fourier cosine transform of this Gaussian function. So let us first denote this function by f of x. So f of x is equal to e raised to minus ax square, and here the Fourier cosine transform of a function is defined by this integral, and the notation for the Fourier cosine transform of a function f of x is given by fc, and here we write f of x, and it is defined by this integral, that is 0 to infinity, and here we have f of x, and then here we have the cosine function, that is cosine sx, and here we have dx, right? So this is the definition of the Fourier cosine transform of a function f of x. So let us write here 0 to infinity, and here for f of x we can now substitute e raised to minus ax square, and here we have cos sx and dx, and here we have fc, and for f of x we can now write e raised to minus ax square, right? So the Fourier cosine transform of this Gaussian function is given by this integral, and now we have to solve this integral, right? And here we have written three important concepts which are going to be used to solve this integral, right? So the first one is the differentiation of the integral, right? So here we have this integral, so let us call this integral as I, right? And let us take this integral I as a function of s, right? So we can also write I of s is equal to 0 to infinity, and we have e raised to ax square and cos s times x, and here we have dx, right? So the first concept is differentiation of the integral. So here we'll differentiate this integral I with respect to s to get a differential equation, right? And will then make use of this important concept, that is integration by parts, right? And then we'll form the differential equation, which is a variable separable form. So these three important concepts are going to be used to solve this integral. So let us first differentiate I with respect to s. So here we can now write di over ds, and we'll use the notation simply I for I of s, right? And here we have d by ds of 0 to infinity e raised to ax square and cosine s times x dx. So now taking this operator inside the integral, we have 0 to infinity e raised to ax minus ax square and d by ds of cosine s times x, and here we have dx, right? So we can now write 0 to infinity e raised to minus ax square. Now see, here we have to differentiate cosine s times x with respect to s, and the derivative of cosine function is the negative of sine, so we have minus, and then we'll differentiate s times x by chain rule. So here we have simply x, and then we have sine s times x, and here we can write dx. So now we'll simplify this integral with the help of integration by parts, right? And we know the formula for integration by parts as integral u dv is equal to uv minus integral v du, right? So let us slightly modify this integrand. So we can now write di over ds, and let us divide this integral by 2a and multiply the integrand by 2a, right? So we can now write here a minus 2ax. So here we have negative x, so minus 2ax, and then we have e raised to minus ax square, and then we have sine s times x and dx. So now we can write this integral as 1 over 2a, then we have 0 to infinity, and we can take sine s times x, and we can now write this term as the derivative of e raised to minus ax square, because the derivative of e raised to minus ax square is given by e raised to minus ax square, and then by chain rule the derivative of minus ax square is minus 2ax. So we can now write minus 2ax, and here we have dx, and minus 2ax e raised to minus ax square dx. So for this term we can write the derivative of e raised to minus ax square. So now di over ds is equal to 1 over 2a and integral from 0 to infinity, and here we have sine s times x, and here we have the derivative, that is e raised to minus ax square. So now sine s times x can be taken as u, and this function as v. So we have u is equal to sine s times x, and v is equal to e raised to minus ax square. So now di over ds is equal to 1 over 2a and integral 0 to infinity, and here we have u dv. So now we can write here di over ds and 1 over 2a integral 0 to infinity u dv, and using this result we have here uv, and then we have integral v du, and limits of integration are from 0 to infinity. So we have 1 over 2a, u times v is sine s times x, then we have e raised to minus ax square minus integral v is e raised to minus ax square, and for du we can differentiate u with respect to x. So du over dx is given by d by dx of sine s times x, and this is cos s times x, and by chain rule the derivative of s times x with respect to x is simply s. So here we have s times cosine s times x. So here we can write s cos s times x, and here we have dx, and limits of integration are from 0 to infinity. So now we can write 1 over 2a, and then here the limits of integration are from 0 to infinity. So here we have e raised to minus ax square sine s times x, limits are from 0 to infinity, and here we can take s outside the integral, and then we have the limits 0 to infinity, and we have here e raised to minus ax square cos s times x and dx, right? Okay, now see this integral is our original integral, that is I, 0 to infinity e raised to minus ax square and cos s times x dx. So we can now replace this integral by I, and here we have to evaluate this expression for the limits from 0 to infinity, right? And from here we can see that when x tends to infinity, then this term, that is e raised to minus ax square, it tends to 0. So for x tending to infinity, this term is 0, and then when we take x is equal to 0, then this term tends to 0, that is sine s times x tends to 0, right? So this entire term is equal to 0. So now we have 1 over 2a, and then we have here 0 minus 0, and then we have minus s times I, right? See, when x tends to infinity, then this exponential term, it tends to 0. So the first term is 0, right? And then we take x is equal to 0. And when x is equal to 0, then this sine term, this sine function tends to 0. So we have the difference of the two terms. So we have 0 minus 0. And here this integral is I. So now we have 1 over 2a, and this is 0, and here we have minus si. So we can take negative sign over here, and here we have s times I. So now we can write di over ds is equal to minus s times I over 2a, and this is the first order and first degree differential equation, right? So by differentiation of this integral I with respect to s, it has led us to this differential equation, right? So now we can easily see that this differential equation is a variable separable form. So we can separate here the variable I and. So separating the variables, we can now write di over I, and then we have minus 1 over 2a, and here we have s and ds. Now integrating both sides. So we have integral di over I, and here we have minus 1 over 2a and integral s ds. Now the integral di over I is simply a log of I, and here we have minus 1 over 2a. The integral s ds is simply s square over 2, and c is the constant of integration. So we can now write natural log of I, and here we have minus s square over 4a, and c is the constant of integration. And now we have to find out this constant of integration by using some initial condition. So now see, when we have assumed this integral as I, then we have differentiated this integral by taking s as the variable, right? So here natural log of I can be written as natural log of I of s, and we have minus s square over 4a plus c, right? Now to get the initial condition, let us take s is equal to 0 in this integral, right? So here I is a function of s. So we have I of 0 is equal to integral 0 to infinity e raised to minus ax square and cos 0 dx, because we are taking s is equal to 0, right? So when s is equal to 0, then I of 0 is given by this integral, and cosine 0 is equal to 1. So we are left with this integral, that is 0 to infinity e raised to minus ax square and dx, right? So now we have to directly write the value of this integral. So by using standard results, the value of this integral is 1 over 2 times square root of pi over a, right? Okay, so now when s is equal to 0, then the value of the integral, that is I of 0, is 1 over 2 times square root of pi over a. And taking these conditions in this equation to get the value of c, we have a natural log of I of 0 is equal to minus 0 square over 4a plus c, and this term is 0, so we have simply c. So c is equal to natural log of I of 0, and I of 0 is half times square root of pi over a. So let us substitute this value of c in this equation. So we have natural log of I of s is equal to minus s square over 4a, and here we have natural log of half times square root of pi over a. So let us take this term to the left hand side. We have natural log of I of s minus log half square root of pi over a, and this is equal to minus s square over 4a. Now using the properties of log, here we have log of m minus log of n is equal to a log of m over n. So here we have natural log of I of s minus natural log of half times square root of pi over a. So we have natural log, and then we have I of s divided by half times square root of pi over a, and this is equal to minus s square over 4a, right? So now using the definition of natural log, we can now write I of s over half times square root of pi over a is equal to e raised to minus s square over 4a, and multiplying this term by half times square root of pi over a, we can now write the integral I is equal to half, and here we have square root of pi over a e raised to minus s square over 4a, right? So viewers, the Fourier cosine transform of e raised to minus ax square is given by this expression, because the Fourier cosine transform of the Gaussian function e raised to minus ax square is defined by this integral, and we have assumed that this integral is equal to I. So the Fourier cosine transform of e raised to minus ax square is given by half times square root of pi over a e raised to minus s square over 4a. So now from this expression, we can easily conclude that the Fourier cosine transform of a Gaussian function of the type e raised to minus ax square is also another Gaussian function, because here we have e raised to minus ax square, and here we have e raised to minus s square over 4a. So here this is a function of x, and here it is a function of s, right? So the Fourier cosine transform of a Gaussian function is another Gaussian function. So now let us make some important deductions using this expression by giving some particular values to this parameter a, right? So if we take a is equal to say 1, then the Fourier cosine transform of e raised to minus x square is given by a 1 over 2 times square root of pi over 1. Taking a is equal to 1, in this expression we have e raised to minus s square over 4 times 1. So the Fourier cosine transform of e raised to minus x square is given by square root of pi over 2, and here we have e raised to minus s square over 4. So let us take the value of a is equal to 2. Then the Fourier cosine transform of e raised to minus 2x square is given by 1 over 2 times square root of pi over 2, and e raised to minus s square over 4 times 2, and this is 1 over 2 times square root of pi over 2 and e raised to minus s square over 8. So the Fourier cosine transform of e raised to minus 2x square is given by half times square root of pi over 2 e raised to minus s square over 8. So let us take a is equal to 1 over 4. Then the Fourier cosine transform of e raised to minus x square over 4 is given by 1 over 2 times square root of pi over 1 over 4 e raised to minus s square over 4 times 1 over 4. So we can now write half, and here we have square root of 4 pi, and then 4 and 4 get cancelled, and we are left with e raised to minus s square. And here we have half. Square root of 4 is 2 times square root of pi, and e raised to minus s square, and 2 and 2 get cancelled, and we have square root of pi times e raised to minus s square. So the Fourier cosine transform of e raised to minus x square over 4 is given by square root of pi times e raised to a minus s square. So now let us take a is equal to 1 over 2. Then the Fourier cosine transform of e raised to minus x square over 2 is given by 1 over 2, and then we have square root of pi over 1 over 2 e raised to minus s square over 4 times 1 over 2, and this is half. This is square root of 2 pi, and here we have e raised to minus s square over 2, right? And this expression can also be written as square root of pi over 2 and e raised to minus s square over 2. So the Fourier cosine transform of e raised to minus x square over 2 is given by square root of pi over 2 e raised to minus s square over 2.